FDL Heliolab has been at the forefront of advancing our understanding of life within the solar atmosphere. Through intricate interactions of magnetic fields, radiation, and plasma between the Sun, Earth, Moon, and Mars, we are now able to explore these phenomena with the power of artificial intelligence. We asked our senior FDL faculty to reflect on the groundbreaking progress, unveiling the science being revealed, and to offer a glimpse into the future of this transformative work.
In many cases that I notice as a reviewer and then as a faculty, the results are very promising. So it does help open some of those bottlenecks that we have in the research. And occasionally, like in some of our more successful challenges, it keeps on giving. You know, the team sticks together, keep coming with new ideas, with the right papers, they interact with the community, and then more ideas come in, which we then ourselves can use in the future FDLs. So it creates like a snowball effect, in my opinion.
I think you get ideas and solutions from this collaborative environment that one person alone wouldn't think about it. That thing is very positive. And also, I think this collaborative dynamics can bring the people from academia that is more used to work autonomously. I think this interdisciplinary way of working could help those to open their minds and have like a broader vision.
The one aspect that I really liked about FDL was the deadline system, right? The internal deadline system. The first thing that I really appreciate. I mean, it gets you out of your comfort zone. You might not realize, you might feel a little overwhelmed while you are in there, but it grows into you over time. And then you don't even realize that you are actually enjoying the process. But the weekly thing or a bi-weekly thing actually helps you keep on track, keeps your work on table, and it appropriate track of your progress.
FDL Heliolab has led the charge in applying AI to space exploration. We extend our deepest gratitude to our advisors, guest experts, and partners, and perhaps most importantly, FDL's exceptional researchers for a decade of inspiration and innovation.
Hello and welcome to Heliolab Live Showcase 2025. Thank you for joining us today. We have some fantastic things to share with you. We know you are going to be delighted with your experience today. This is our state-of-the-art AI showcase. And boy, is it ever. We will hear from a variety of our researchers and others as they share their research results. Now, as every good mission needs a good co-pilot, I can't imagine a better one today than my very good friend and colleague, Scott Penberthy. Scott, why don't you join me here on stage for just a moment? Hey, my friend, how you doing?
Hey, morning, Jonathan. How are you? I'm really looking forward to today, buddy. It's going to be great.
Thank you. This is going to be great. You know, for those joining us today, Scott and I have known each other for several years now, and we've been riffing and talking about a lot of these things that we're going to talk about today for some time. And for those of you in the know, I don't know if our European colleagues get this or not, but Scott said, I totally get it when I asked him if he'd do this. Mystery Science 3000 theater style. And that was great. Yeah,
we're gonna have fun today. It's gonna be good.
we are. Well, thank you. Hey, Scott, we're going to bring you back up in just a few minutes. We're going to do a few things right before you. Thanks again for being here, and we're off to the races here. So let's talk a little bit about how we're going to go through things today. We will hear from some of the representatives from our Heliolab partners at NASA and Google today, followed by our researcher presentations, and then reflections from a variety of notable scientists. This is also a chance for us to celebrate the summer of research, and we'll be having our annual collaboration awards at the end of the presentations. So do stand by for that. That said, I would love to kick things off with another dear friend and collaborator who has been that for many years now. Leika, if you would please join me up on the stage today. Thank you for being here. And I'm so glad you chose the Corona background. Every time I see it, I just think, I can't imagine anybody has a better background for these kinds of events than you. And the way you position yourself right in there, it's just great. Well, thank you for being here. I'm sure you're going to enjoy this as well. Now, we wanted to ask you a few questions before we get started. I hope that's okay with you.
Thank you, Jonathan. And I call this is the only thing you have that's unique about the picture, a human head as an occultor blocking the sun.
I love it. And that's exactly what it is. It is. That's highly accurate. Well, as I said, it's an absolute pleasure to have you with us today. You've been at NASA for multiple decades. That's because you started when you were 10, I think, clearly. You've been leading and contributing to some of the most significant missions in heliophysics during that time. And now here you are with us today as we're about to hear from the 2025 Heliolab teams whose work, frankly, pushes the boundaries of AI. And my first question to you is, what excites you the most about seeing AI and heliophysics come together in the work we're going to hear about today?
So much, so little time. You know what excites me is that we are actually watching two fields, once seen as separate, right? Finally dance in close step. And heliophysics gives us the rhythms of our living star. AI gives us the tools to improvise with those rhythms in real time, kind of like your jazz at Las Gatas. And then these projects just don't use AI to analyze solar data anymore. You know, they are reshaping how we ask questions. That's kind of is really something very deep, very profound, I believe. And that's the revolution. We are no longer spectators of solar variability, because we have been for as long as, you know, humans existed. We are basically becoming co-inquirers, able to test, refine, and respond to the sun's behavior with the level of speed which we can only do with the participation of Google, which we so appreciate, and nuance that was unimaginable a decade ago. And so I think these are just not new tools. It's a new grammar for solar physics, for heliophysics. It's a language written in patterns, you know, priors and predictions. And that's what you're going to see unfold. It is really an exciting moment.
I couldn't agree with you more. And I'm wondering if it's possible, without giving too much away, if you can think of any particular elements or element of this year's work that you think might surprise even the most seasoned heliophysicists and data science that are joining us today.
So, I mean, you know, I've been at NASA for a long time, watch, you know, demos of solar sails unfold, instruments ride eclipses across oceans, continents, and even space, and spacecraft like Parker Solar Probe kiss the corona. But Heliolab, this is actually a different kind of launch. So in past milestones, as you're asking, the question would often be, we built the instrument, now let's see what it shows us. Today, I think that story is we built this model with AI inference and observations from space and ground, and now let's see what it teaches us. So I think this is sort of a pivot point. We are not just documenting the sun's moods, we are creating the means to anticipate them. And I mean it, and not all of these results will be showed here today. And you know, we are collaborating across data streams and design systems that evolve with the science.
Certainly. Is there anything you think that people should be watching for or listening for that might spark new ways of thinking or new collaborations for the work that they're doing?
Certainly. I would say that there's just so much to be surprised, right? These are there's a myth that AI is a black box. But this year, we've seen things like foundation models that don't just spit out, you know, answers, they reveal structure. And, you know, that's the part that's going to be coming next week. We are doing magnetic topology maps, temporal attention heat maps, language-driven solar searches. We are not just getting results. I think we are seeing new ways of representing the sun and its connected system, ways that feel like a Rosetta Stone for solar variability. And so I'd say in Heliolab, we don't just use data, right? We are actually conversing with it through AI inference models. So if there is one little giveaway, I'd say the Orchestrator challenge. These are all amazing challenges, but that one, that's not just science, that's symphony.
Ooh, I do like that. Okay, well, thank you. Your perspective definitely always adds so much meaning to the things that we do. And we're going to bring you back up at the end after everybody's had a chance to share their work and hear a little more from you. So thank you for joining us, Leika.
Thank you.
Of
and
course.
Good luck to all.
Thank you. And a big thank you to all of our partners, certainly NASA, one of the founding partner, and our other key partners, Google Cloud Platform, NVIDIA, and Pasture Labs. We truly couldn't do it without them. And we have had this relationship with these partners for many years. This is our 10th year of Frontier Development Lab of FDL. If you can believe it, it's a little hard for us to believe it sometimes, but here we are, 10-year anniversary, and we're going to kick off. Before we hear from our researchers, we're going to bring Scott back up. Scott, if you'll join me.
Hey, I'm back.
Hey.
I'm aboard my ship now, Jonathan, thanks to
I love it. Oh, yeah. And I love that you put
so
that
we're zooming in
there.
on the stars, so we're getting pretty close. It's a little hot in here, but I got air conditioning, so we're good.
A little toasty.
Yeah,
that's
toasty.
Nice.
Yeah.
Well, one of the things, you've been doing AI. First of all, Google's been at the forefront of AI for quite some time now, and you've been in the AI domain for many, many years. And over the last several years, how many did you just say?
Yeah, too many.
Too many, yeah. And over the last few, you and I and others have spent a lot of time thinking about and talking about discussing the future of not just AI, but we've sort of zoomed in a lot recently on AI for science.
Mm-hmm.
And that seems to excite us all. And I'm wondering if you can share to start, what excites you the most about what you think is possible, what you believe is possible for AI for science, what you'd like to see.
Yeah, it's super fun, Jonathan. You should also check out, our fearless leader Demis, who just did a podcast with Lex Friedman, who says the same thing. It's pretty interesting. I call it the MIT thesis. And what's interesting is nature is not random, and nature has these patterns. And what we're finding is that with sufficiently large, these basically a combination of transformers and diffusion models, we're able to basically through neural networks find those correlations and then find the generations. Which means pretty much anything in our observable universe, I do mean anything, we can now start to approximate now through these large neural nets. That's exciting. And what's happening now is that AI for the first time is starting to become a tool of science. And I think your scientists are teaching us a lot about, well, how do you actually use this? We're seeing things where if you think of the analogy of trying to understand love and creation and, physics through the lens of a pixel, VO3 recently produced that has remarkable understandings of fluids and fluid dynamics without actually being taught the equations of Navier-Stokes, right? And that's remarkable. And we can do the same thing now at a very small scale with cancer and predicting how a protein folds the ligand. That was a Nobel Prize.
Yeah.
And so I think we're just starting to see now with your help is like AI is finally what we want to do, which is becoming a true tool of science, trying to understand the substrate that we approximate through Navier-Stokes and things like that. But there's something interesting we're finding with these neural networks that we're trying to discover. And it's pretty amazing. And we think that this is now going to be, Demis nailed it, I think, almost 20 years ago. I think he said it might take him 20 years to create a tool where AI is a true tool of science. And now we use that to solve everything else. Right.
Yeah.
And that's what we're on the cusp of that. And it's one of the most exciting times.
What do you think it looks like? Like describe a scenario on how a scientist and AI, go, maybe it starts as tool and where does it go after just a tool for science?
Some fundamental questions in science that we're going to start to approach, can you do NP problems with pre-training on a polynomial space, right? So things are just intractable before. Can we sort of do it in this polynomial space with these neural nets? That'd be extraordinary, right? So a lot of, I think, these things that escaped us, not quantum, but the observable universe will start to, it may be in the next few decades that, what do you mean you don't understand how that works, right? And where AI is, and AI basically helps us solve a lot of, core questions in physics and in science and in biology, where now we can go after the harder problems, things about what is dark matter, right?
Yeah.
How do we connect across time and space? Is this a simulation? It's like really get into those.
Right.
And I think it's the kind of things where, sending robots into space that we can interact with in real time through these other mechanisms is within our lifetime. And that's super exciting.
It really is.
I think you talked about last time, we have robots now parachuting literally,
Mm-hmm.
in the air of Mars because they don't have to worry about, atmosphere, right? And now it's humanoid robots to build something for us. And I think that's robotics plus AI is the future of space exploration. We're starting here today with heliophysics.
Exciting and amazing don't even capture it for me. It has to be other words more than that, because it is so wow. It's
like we discovered bacteria or discovered the microscope.
Exactly.
Like, what is all this? And so
That's
now scientists now are using that, as we'll see today. They're starting to use that in ways is like that's just another tool of science or a collaborator for science.
Yeah.
Right?
Okay, so the researchers have been using AI as a tool for science, and we're going to kick off the presentations now. So at the end of each of the presentations, you and I will be joined by these notable scientists from data science field and heliophysics, and we'll get some reflections from them. Sound good?
Yeah, I'm super excited to learn from them today. Let's get going.
Yeah. Okay, let's get going. So let's do this. Let's get started with our first team, but here is the list of all of them that we are going to be hearing from today. Let's get started with Team Arcade, Active Region Characterization and Analysis of Dynamics and Evolution. Welcome to the stage, Team Arcade.
Hello, everyone. We are Team Arcade, and we're really excited to share with you the work we've done this summer to try to improve our understanding of the complex physical processes occurring in the sun and how they create the so-called space weather events that can have a dramatic impact on our life here on Earth. When the sun emits high-energy particles and electromagnetic radiation during the most powerful solar flares, it can harm electrical grids, satellites in orbit, and expose astronauts in space to potentially lethal doses of radiation. The earliest indicators of solar eruptions that lead to space weather events originate in the sun's magnetic field, especially through the emergence and evolution of so-called active regions, where the field becomes twisted or unstable. Therefore, it is important to build a model that forecasts the future state of the magnetic field to provide an early warning of solar activity before it turns into a hazard. To achieve this goal, we combine existing physics-based predictions with novel data-driven AI insights to build the most accurate and reliable forecasting of the emergence of active regions hours in advance and for the very first time. The spatial and temporal evolution of the solar magnetic field is currently predicted through sophisticated modeling of 2D surface magnetic flux transport, which is controlled by the physical processes of advective and turbulent transport, as well as the emergence of new regions of magnetic flux. To assist with this research, many space-based observatories, most notably the Solar Dynamics Observatory, have generated petabytes of multimodal data to probe the numerous physical processes underlying observed solar activity. However, too much of any good thing ultimately comes at a cost. At present, traditional statistical models struggle to handle this volume and complexity of data. Therefore, the field has moved towards the adoption of AI and machine learning to extract the full predictive power necessary for accurate and reliable space weather forecasting.
Now, I'd like to put the research part of heliophysics and AI in some historical context. As Nina mentioned, we've been sending out probes like SDO to study the sun for decades, and this has led to a massive influx of data. Concurrently, our abilities in large-scale data analysis have absolutely exploded, especially in the years since SDO launched. This has given rise to modern AI techniques like generative AI, transformers, and ResNets. Our most recent approaches to SFT modeling, AFT and ADAPT, both were initially developed around 2014, and we still consider these to be the state-of-the-art or Sota today. However, these are well before the massive paradigm shift in scientific data analysis induced by AI. So we really haven't had the ability to address these long-standing challenges until now. Arcade explicitly addresses hurdles in accurate SFT modeling and modernizes active region forecasting for the AI age, while still taking advantage of existing knowledge in heliophysics. First of all, we incorporate multiple UQ techniques throughout our forecasting pipeline. We also cleanly integrate AI with existing mathematical models developed by heliophysicists. Finally, we establish successful short-term forecasts on the order of 6 hours in advance. Now, let's start getting into some more technical detail. We start by incorporating a wide range of solar data modalities, seen here. We then fit parameters and mathematical models to this data, as well as train neural networks to aid in numerical forecasts. And what this gives us is a deterministic forecasted magnetogram. And then, after prediction, these outputs are passed into another neural network, which returns Gaussian means and variances over the predicted magnetograms. This probabilistic perspective makes our results more interpretable and trustworthy to scientists and stakeholders. Altogether, this gives us what we want: data-driven, UQ-enabled magnetogram forecasts.
And as we design this workflow, we need to address the long-standing physics and AI divide. Because you know how physicists like to think in terms of equations that describe physical processes and in variables and parameters that can be empirically measured by instruments. Well, you see, deep learning models, on the other hand, can be huge and complex, and that sometimes makes them hard to interpret. So it stands to reason that these decades of petabytes of data stored in public repositories hold massive latent value if only AI models could scan them for patterns and do so in the language of physicists. And to do that, we created a model that takes in measurements of the solar surface as images and uses that to predict the future motion of active regions. The model solves the governing physics equations for surface flux transport using a ResNet. And the parameters that it learns through the model are used to create future forecasts. Here you can see what the input to the model looks like. It's a square image of the sun taken by instrumentation in space. And here you can see how the magnetic flux emergence is forecasted 6 hours into the future by our model. And you can compare it here with the full forecast from the target observation data. And here in the blue, lastly, you can see in the blue spots where uncertainty is quantified by the model. We call this arcade. And you can think of it as a real arcade where multiple systems come together, each bound by its own set of rules under a unified system to create a cohesive model of reality. This model is the first to marry AI and physics in this way. And it gives us interpretable equations, a cloud-native architecture, and a scalable framework that we can use to continue to advance on the state of the art.
Arcade, a novel approach that extends traditional SFT and physics-informed machine learning frameworks, as Plinio mentioned. For the first time, this enables uncertainty-aware forecasting of active regions. This capability opens new doors. With the development of high-resolution instruments and continuous solar monitoring, we have now access to vast volumes of high-quality data. For the first time, we can observe fine-scale structures and evolving patterns in active regions with unprecedented clarity of several solar cycle worth of data. By continuously integrating SDO observations and adapting flow fields using a combination of machine learning and space-based modeling, as shown in this demo, we move closer to operational forecasting and magnetic activity. It opens the door to predicting not just the transport of magnetic flux, but also the timing and location of new active region formation, which are key precursors of solar flares and CMEs. In short, Arcade approach represents a step forward in data-driven space weather modeling, one that blends physical realism, the adaptability and efficiency of AI, and uncertainty estimation to provide tools critical to both scientific research and practical forecasting. Arcade now enables us to understand and forecast the near future of Sun, giving Earth an earlier warning that it had to prepare for change in the Sun. Finally, we would like to thank our sponsor, Google Cloud, for making this project possible, and the ARC team for making their simulation openly available. Thank you.
Well done, Team Arcade. Good stuff. Hey, Alessandro and Asti, why don't you join us up here on stage? Alessandro is a senior simulation intelligence engineer at Pasture Labs, and Asti is a senior research scientist at SRI International. It's good to see you both. Thank you for being here today. And let's start by getting some thoughts from you. I'll start with Asti because you're first on my little list over here. What do you think? Here we are making predictions. It's wow. Wow. When you consider how young heliophysics is as a modern science, what do you think about this research from Team Arcade?
I think it's extremely exciting. This is sort of the new frontier in how we are doing the active region characterization. This sort of work started few years ago, and now I think this team has taken it to the next level. So I'm really excited to see where you can take it.
It is exciting. And Alessandro, what do you think? Was there anything that jumped out specifically for you as you listened to this?
Yes, actually, I think one of the
things that like is very natural when you see like these very complex projects, right? Is that a lot of the components that you have there are like sort of packaged into neat boxes that like we think that are like, you know, sort of like simple to then interconnect, but actually being able to sort of like make this jump from like, you know, I have like this small component of like a system, like one of these predictions so that we've seen from Arcade, like, and sort of like integrated into a larger system. To me, that is like one of the like biggest challenges also like continuing to develop this sort of like inference or prediction pipelines and, you know, continuing to have good results in that regard.
Absolutely. And Scott, I mean, thank you, Google, for providing the guidance and the other stuff we need to do this research. What do you think about how the team's done so far?
Yeah, it's dope. What I like, Jonathan, about this is that look what they've done. You have so much data that it chokes original methods, right? So now you need this new approach, and they've used sort of a ResNet, which is sort of like, you know, a step towards the models like the transformer heads plus the diffusion heads that are happening. And what's really interesting is we're trying to figure out how do you create a physics model to actually understand inside these models. And they've got a neat blend here, which is like, don't go all the way, start with a ResNet and then actually start to use equations and have them come together. So I think we're starting to get towards this convergence of, you know, science plus these neural nets. And I'm really curious as they continue this research, how far can they take that, right? So you have transformers diffusions coming together in what we call transfusion models. That's relatively new, last few weeks. But as they're looking at science, how far can you go? You know, I don't know the answer, but I think they made really good progress here, saying let's take a step forward in the neural network, a step forward in science, and they have the very neat blend of magneto models, right, differential equations, as well as the two feeding together, very novel. And then I encourage them to figure out, you know, keep pushing that. You know, how far can you go, and is there something in the neural net that can actually replace those? I don't know, right? MIT says there is. I think we need scientists to really weigh in, like Asti and others.
I think it's always good to say, I don't know. It's a perfectly good thing to say because we're going to always follow it with, let's find out.
Right.
Let's find out. And
science find out. Is that what you say? Science
find out. Yeah. And Asti, so what's the big deal about predictions? So why do we care that we get this right when it comes to the work that the Arcade team is doing?
Well, the fundamental answer is we don't know, right? If you don't know, our job as a scientist to find out. And I think what excites me most about this team's work is the blend of the fundamental physics and the AI, which is actually, it's part of their model. And I think they've done a really good job in describing that aspect. Why it is important to predict is that because when we live with that sun, and everything that happens on the sun has direct impact on us, and especially now that we are in this technological society where everything depends on the space environment, the space environment gets severely affected by all of this. So I think this is going to be the next frontier to use.
Yeah, thank you. And Alessandro, the power of simulation, right? It really is astounding when you think about the kinds of things we're now beginning to be able to do.
Yeah, I mean, and simulation especially, right? Like in a sort of like a principled manner. I think like also like all of the other panelists before me like also said this in one way or the other that you need in this like scientific approaches like to like in these scientific applications of machine learning. You do need to sort of like not treat your system as a black box. Also, probably like respect to my previous comment, right? Like you always have to sort of like have various components, which sometimes may be, let's say, pretty like the newest transformer model that you can fit like on this scientific data, and other times it's maybe, oh, I have a black box solver that it will be like too messy to rewrite, or just this is a small project that I have to do. So how do I integrate, let's say, these various parts together? And I do believe, however, that at least in the short term, like, there's going to be a lot of like, sort of power that like simulations and physics-based simulations give to machine learning approaches. Basically, like the two really have to come together to generate meaningful results.
Yeah, nice. Asti, can I ask you another question? Do you have any advice for the aspiring heliophysicists that are with us today and aspiring heliophysicists that are watching this, perhaps?
All I'll say is that don't let your curiosity die. Lots of things happen during your lifetime in which things will tell you, external factors will tell you that, oh, you have to really focus on the application, which is important, but it's also important to keep your curiosity alive. Otherwise, the application will suffer and the curiosity will suffer and everything else. So, yeah.
Wonderful.
Alive.
Keep your curiosity alive. Absolutely. Okay. Thank you all. And we're going to move on to the next presentation now. So with that, we will look at team flare prediction. Team flare prediction, let's take the stage. It's all up to you.
Good afternoon. We're the multi-model flare prediction team. Over the past 8 weeks during our FDL sprint, we've achieved results that we are confident that will capture interest and demonstrate the potential of our approach. Here's a quick look at our team FLUXES, which stands for Framework for Operational X-ray Emission Synthesis. My name is Allison, and together with Jayan and Griffin, this summer we worked together how we can use artificial intelligence to better understand solar flares. We're very lucky to be guided and supported by our amazing faculty mentors, Angelos, Christoph, and Lorian, with Robert as our great advisor. Now that you know our team, let me set the stage by explaining what we are studying. Solar flares are sudden bursts of energy released from the sun. Although they happen millions of kilometers away, their radiation can reach Earth within just a few minutes. Those flares can disrupt satellites, aviation, GPS, phone signals, and even power grids, which are vital in our daily lives. They can also expose astronauts and spacecraft to harmful radiation. That's why we monitor solar flares using satellites like GOES instrument, measuring the soft X-ray flux in real time, which is a key indicator of flare strength. But there's one limitation. GOES provides integrated measurements of soft X-ray flux, which makes it challenging to identify the locations of flaring events on the sun. This leads us to ask this question: is it possible to identify the locations and strengths of flares simultaneously? So to answer this question, we need complementary data that can provide spatial information. This is where NASA's FDL AI data steps in, which provide extreme ultraviolet images of the sun. Those images can tell us where a flare is happening, where GOES provides us with information about flare strength. But this requires running two separate systems. So the challenge is, can we somehow extract both flare strengths and locations from just using FDL AI images data alone? The answer is yes. The solution is our FLUXES model, which can accurately learn the translation between FDL AI data and GOES soft X-ray data, while still extracting flare locations, essentially giving us a virtual GOES instrument on board of FDL AI. This opens up some exciting possibilities, as we can now apply our FLUXES model to extreme ultraviolet image data from viewpoints beyond Earth's line of sight, such as those provided by stereo instrument. In doing this, we can estimate the strength of flaring events on the far side of the sun, which can ultimately improve future event forecasting and enhance our ability to protect astronauts in space. So again, our big question is, can we figure out flare's soft X-ray flux just by looking at extreme ultraviolet data? To dive deeper into how we can tackle this, I'll now hand over to Griffin, who will walk you through the methods we're using and explain our approach in more detail.
Thanks, Allison. So to explore this question, we turn to artificial intelligence and machine learning, which are techniques that have become widely adopted in the fields of heliophysics and space weather. If you're unfamiliar with these concepts, here's the basic idea. Machine learning models are essentially mathematical algorithms that learn patterns between an input and an output. And once the algorithm has mapped the patterns in the data, it can then be applied to new input data that we provide it with, to then make predictions on an unknown target value. So in the case of this project, the data we're inputting into our model are these extreme ultraviolet images. And given that images are just a combination of numbers, so things like pixel locations, and their brightnesses, these images can be fed into our model as numerical data. And then the output, or the target value, is then the associated soft X-ray value for the given stack of images we provided. Our Fox's model utilizes a specific class of machine learning architectures known as vision transformers, which we've trained on Google Cloud Platform using NVIDIA A100 GPUs. These models work similarly to how many large language models work, such as ChatGPT, Google Gemini, and Claude, except now, instead of taking in sentences as input, the model accepts images. You might be thinking, how exactly can an image have any similarity to sentence structure? Well, if we take our solar images and we segment them into many smaller cropped images, also known as patches, each patch acts almost like a word in a sentence, and adding all these patches together gives us our full sentence, which is essentially the entire image. And so feeding these patches into our model, the algorithm learns complex patterns between each patch, allowing it to accurately model where on the sun it needs to pay attention to in order to make an accurate soft X-ray translation. And thankfully, one of the key benefits of this architecture over others is that the model actually tells us where it's looking. So this means we can get interpretable predictions, giving us potentially better spatial localization for where flares are occurring. And next, I'll be passing it over to Jayant, who will be discussing some of our results.
Thank you, Griffin. After all the extensive work we have done on data preparation, model development, and evaluation, we have finally arrived at our results. Foxes is a tool that not only detects solar flares, but also tells us where they happen, when they strike, and how strong they are. Take a look at our video demo here. On the left, you'll see heat maps from Fox's pinpoint flare locations on the sun, perfectly overlaid on 6 wavelengths of real solar images. On the right, a graph shows X-ray energy over time. The orange line here is real satellite data. The purple line is models predictions. And as you can see, our ground truth and predictions align consistently, especially for high intensity flares, ensuring reliable translation. But what's even more impressive here, Foxes can predict flare strength even when ghost satellite data is missing. This fills critical gaps, ensuring we are never blindsided by solar activity. For space agencies, satellite operators, and researchers, this precision is game changer for real-time flare detection and response. But why should you trust Foxes? This slide shows our model's reliability. The color band here represents prediction error rates across different flare intensities. The closer they are to the diagonal line, the better we are doing. Look at the green and purple bands here. Those represent the strongest, the most dangerous flares, and you can see they are practically glued to the line. This means Foxes delivers when it matters the most, giving us confidence to translate high-impact solar events accurately. For mission planners and space weather team, this reliability means better preparedness and safer operations in space. So to summarize, our Foxes model can take extreme ultraviolet images and convert them into soft X-ray flux with incredible precision, capturing both rapid onset and gradual decay of flares. But we are just getting started. Our next step is to create the first ever multimodal flare catalog by applying Foxes to data from missions like Stereo. And this will let us translate flare strength from angles beyond Sun outline, a revolutionary leap for the future of flare forecasting. So now imagine the impact. Researchers can now improve current flare forecasting models as they now have access to richer catalog of flaring data, and in addition to this, space agencies can now make reliable predictions for missions far from Earth. With NASA's Artemis program pushing towards Mars, Foxes will be critical for protecting astronauts, satellites, and other assets in deep space. So this is about enabling the future of space exploration. Thank you.
Well done, multimodal flare panel. Just fantastic. Yeah, and And yes, the future of space exploration, right? This whole domain of heliophysics is one of the things that we have to do if we're going to explore space. We want to bring up Dan from JPL. Dan is program manager at JPL, NASA JPL. Hello, Dan. How are you today?
I'm excellent and just really enjoying the talks. Thank you.
Well, glad you were able to join us here today. I'm not sure if Brian is the acting staff scientist at NASA's Solar System Exploration Research Virtual Institute. Now, he, I believe, was on site at NASA Ames today, and when we did some testing earlier with him, he was having some network issues. So we'll see if he manages to join us in just a little bit, but I suspect that's what happened. So, but we have Dan. So here we are, and JPL, right? JPL is talk about space exploration. You guys know a thing or two about that.
We do, and we recognize the opportunity we have with artificial intelligence, really to figure out how do we advance the science discovery, and in really what's happened with increasing computation and our ability to be able to apply these algorithms. So we're excited to see the progress.
Yeah, it is something else. Scott, did you have any thoughts as you watched the multimodal team?
Yeah, I'm still going back to their diagonal lightsaber, Jonathan. If you look at how tight that 95% interval was, and they just talk with aplomb, basically using, I'm just doing high dimensional non-linear correlation. What's the big deal? I mean, it's just how it just rolls off the tongue, how they're just using AI as a natural tool. I think that Dan is phenomenal. And now they're treating it just like another tool in science. And, I think it's really interesting to see now the animations they're doing, how AI is now able, to guess the missing data, which has always been a pain, Dan, right? You're missing big chunks of data in these, very expensive sensors just because of life. It's just really interesting to see how far they've taken it. And that is for those scientists to know, that's a very tight 95% confidence interval, right? For correlation.
Yeah. Hey, Brian, I was just explaining that you were having some network issues. I'm glad you overcame them and were able to join us. I think. Can you hear us?
Almost.
There you go. You're coming in. Give me one more chance to let me see if I can hear you. Well, while he's doing that, I will ask Dan. You've been a part of many different missions over time, and I wonder, did you ever think we'd get here with some of the things we're doing with AI, and what do you think about the role it's really going to play when you think about the kinds of things AI does? How will people let's say Gentry Lee was still making things there at JPL. How would people like Gentry use?
Yeah, I mean,
tool?
the reality is, I think, I dreamed that we would be here. I never really probably thought we would be here. I think that we've seen a massive acceleration and capability that's occurred the last few years. Models are getting much more sensitive.
Mm-hmm.
We're able to do so much more with the data that we have. And, I think as we look at future missions, we're going to be able to use the data to really drive and make decisions about what kind of data we want to acquire and what science we can get back. And that integration is something that we got to figure out how to bring together. So having our teams of data scientists and scientists working together to create these AI projects. This is the beginning of a new era, and I think it's going to help us move forward.
I think you're right. Yeah, I think you're right. Scott, thoughts on what Dan just shared?
Well, is Brian's mic working yet?
Brian, can we hear you, Brian?
Yeah.
Oh,
yeah, I am hearing you. You're kind of coming in and out. Are you hearing me?
We are hearing you now. Great. Thank you. So let me jump over to you for a minute because, one of the things that we want to help our researchers with, in addition to just doing the research that needs to get done, is two things: the importance of how to communicate and share that information. And I'd like you to touch on the importance of that. But I'd also just like to share that you are, I was going to say an aspiring heliophysicist, but maybe you're even an amateur heliophysicist.
Yes. Okay. I'm going to take a crack at this. It's kind of cutting in and out for me again, but I'll cop to the fact that I am a professional lunatic and not a heliophysicist. My daily work deals with the moon, and I've been very pleased to see previous efforts by FDL on the moon. They've been very instrumental. We've integrated some of that into our projects, but it is very, very, very exciting to see this work being done with the sun. Great case in point is Solar Cycle 25 outperformed many of our predictions. It was supposedly, in many of our minds, going to be this very minimalistic solar maximum. And the beautiful aurora that we saw from right here in the Bay Area of California certainly belie that. So it's there's clearly important room for advancing our understanding and our ability to predict.
Yeah, certainly. And as Leika likes to remind us, I said, hey, we're going to invite Brian Day to be one of our panelists here. And she calmly responded, well, yeah, of course, the moon's within the heliosphere. Everything's within the heliosphere. Everything is part of this thing we call sun. So, but here, my second question to you, Brian, is this notion, because I think you and Joe, our good friend at Ames, along with you, have a lot of experience also in how you communicate and how you bring others along on the science journey. And if you perhaps could just share for a moment your thoughts on the importance of getting that right, as well as the actual research you're doing.
Well, absolutely. These are certainly interesting times for those of us in scientific research. And as we as a society make decisions about where we are going to focus our efforts and our resources, we can't just limit ourselves to dealing with our own, in my case, lunar science community or the heliophysics community, but this has to be something that we do as a society. We will not see the investment in these technologies, in this research, without winning the hearts and minds of the general public. And so it is very, very important to bring them into this endeavor. Now, Jonathan, you mentioned that I am kind of an amateur solar astronomer, and that's one of the really amazing things that has happened now is that the technology has made it possible for the general public to be able to see things, to observe things, to study things on the sun that were not typically available. And so we can now actually observe solar flares through generally available equipment. And this is something that has entered the realm of the amateur. But what we need is the experts to explain the context, to explain the importance, to explain the relevance. And fortunately, the sun puts on one hell of a good show. And
boy, doesn't it?
So we can take advantage of that. And but one thing I would also add is it's really important right now. I mean, yesterday, the acting administrator of NASA, Sean Duffy, pointed out that all of NASA science will now be devoted to exploration. That is an important message for us to hear.
Yeah.
And as we plan our path forward, how do we advance our research? We have to make sure that we are very explicit in explaining that as we plan to have extended human presence on the moon, on Mars, and in these long transits, this kind of predictive capability is essential in order to make that happen. And I think that has to be brought up to the front and center. That's really what we have to communicate right now in this environment. That's what we have to communicate right up front, is that for these goals to be realized, these are essential technologies.
You know, something Leika has been telling us for 10 years. That message right there. So I bet she's real happy to hear that more and more people are coming along to realize just how important that is. And by the way, this photo right here behind me, I took that image myself, so I'm a little proud of that one. Brian, thank you. Dan, thank you. Scott, thank you. We're going to move on to our next team right now. Appreciate your feedback here. Up next is Team Decoding Solar Wind. Team Solar Wind, will you please take the stage?
Hello, everyone. We are the Decoding Solar Wind Structure team. This summer, we've been working to better understand solar wind structures using cutting-edge tools and unprecedented data. The solar wind is the continuous outflow of particles from the sun into the interplanetary space. Within it, we find a variety of small to large-scale structures depending on the sun's conditions. And they all have different properties like speed, density, magnetic field, and more. Solar wind is important because it can cause geomagnetic storms that can affect satellite orbits, communications, navigation systems, and others. It is also the background on which more extreme space weather phenomena propagate. Unless we achieve a good understanding and prediction of the solar wind, we cannot comprehend and predict these severe phenomena as well. The solar wind changes in seconds, producing an ocean of data, now measurable closer to the sun than ever before, that can be analyzed using groundbreaking computational tools and powerful AI models. This let us study solar wind structures at a scale and detail never achieved previously. That's why what we are doing matters. It is important now, and it has not been done before. Therefore, we merge state-of-the-art machine learning with rich, multi-source, unique data to systematically classify solar wind structures, pushing the boundaries of what's possible in heliophysics research. Now, Jasmine will introduce the data sources behind our project.
Thank you, Daniela. So as she mentioned, there's a lot we want to know about the solar wind and how it behaves. This is where we take an interest in one of the most novel spacecraft missions, the Parker Solar Probe, or PSP for short. PSP is one of the main missions dedicated to study the solar wind and its origins. To do so, it measures properties of the solar wind, including, but not limited to, measurements of magnetic field, flow speed, density, and temperature. These are some examples of the in situ observations we need to use in order to identify these solar wind structures that we're interested in. In order to use such data, we did an extensive data preprocessing step to create a PSP ML-ready dataset. This new PSP ML dataset combines measurements from the PSP instruments, including fields, SPC, and span-I, which are then interpolated and ready to be ingested by any machine learning model. Then, using big data preprocessing, quantum ML, and Bayesian analysis, we also analyze PSP parameters to spot invalid data, define accepted ranges, and detect anomalies, enabling smarter choices to train our ML models. Then finally, using these solar wind observations, we compare the PSP preprocessed data with the images observed by the Solar Dynamic Observatory, also known as SDO, to uncover the drivers and precursors of the solar wind structures. Next, Valmir will introduce the approach to decipher such solar wind observations.
Thanks, Jasmine. To make sense of the PSP time series data, we need to check all the parameters depicted here in the time windows. As you can see, it's not obvious how to characterize each part of the time series. With the Cipher pipeline, our new framework methodology, we have been able to characterize each part of the time series in a semi-automated way with a human expert in the loop. The shaded areas here correspond to different solar wind structures. Our method starts with a time window for a given parameter. Then it automatically breaks them and assigns a symbolic index word, and it's showed here in the animation. Finally, using the index word, we can clusterize each part of the selected time series PSP parameter to then classify the entire data set. The cipher operates in 4 stages: compresses the time series, clusters the segments, review results with a human expert, and classify the entire data set. We have the following categories: fast and slow solar wind, and stream interaction regions formed when a fast stream overtakes a slower wind, creating a compression region. Another common event is a coronal mass ejection, when the sun produces a huge burst of plasma and magnetic field into the outer space. Finally, we have switchbacks, events when the magnetic suddenly rotates and changes polarity. Now, we created a new SIR and switchback catalogs, and we have also found a CMEs that have not been cataloged before. Now, Jinsu will present our classification branch.
Thank you, Barmir. We are using SDO-FM, a foundation model trained on SDO images using Google Cloud TPUs. Foundation model like SDO-FM learn representation directly from the input data, enabling powerful downstream tasks with minimal training. The left portion of SDO-FM corresponds to the encoding network, capable to condense information from the input data, which is stored into an artifact called embedding. Using the SDO-FM encoder from a pre-trained network as backbone, and adding a deep classification network after it, we can classify solar wind structure using less data but achieving higher performance. Our model combines 3 sources of data: PSP position data, which is encoded with Fourier features, SDO images, and cipher labels. The combined PSP and SDO is fed into the neural field model to classify solar wind structure using cipher labels as ground truths. We trained our entire architecture using Google Cloud 8100 GPUs and DGX server from NVIDIA. Next, Connor will present the classification result.
Excellent. Thank you, Jinsu. Our model was designed to predict the solar wind class at PSP's location using only SDO images of the solar disk. This means it can capture the physics of solar wind generation and propagation across the heliosphere just from pictures of the sun. Our model isn't limited to just PSP predictions, though. By leveraging neural fields, it can study the solar wind anywhere in space. Here, it predicts solar wind types across the solar surface, shown as these colored dots on the sun. Different regions emit different types of solar wind. We can also use our model to zoom out to study the entire heliosphere. Here, the same solar wind types are shown throughout the heliosphere from above the sun. This lets us predict the solar wind impacting Earth or any spacecraft or planet in the inner heliosphere. Our project has produced a great deal of very useful things for the heliophysics community. As part of training our model, we developed a cleaned, labeled, ML-ready data set by combining data from 3 different instruments aboard PSP. We developed the flexible and extensible cipher pipeline that can be applied to any in situ solar wind data. Using this pipeline, we produced a catalog of labeled solar wind data from PSP and Omni ready for heliophysics analysis. We've dug into the massive volume of PSP data to derive new insights to help heliophysicists better understand exactly what it is that PSP is measuring. And this is, of course, not to mention that we also created a solar wind prediction model based on the SDO-FM foundation model, ready to be used for science and prediction tasks. Thank you very much for your time and for your attention.
Well done, Team Solar Wind. That was, yeah, Scott, I see you smiling there. Isn't that something?
That's something else. You know, I just, I love their optimism, Jonathan, you know, because in AI, there's old adage, like 80% of the work is like labeling data and cleaning it up, you know, and the other 20% is complaining about it, you know, and so, but they did such a great job, and, you know, what they've done with auto regression and just, you know, great result.
It really, really is. Well, let's bring up our next three honored guests, notable scientists all. I'll start by introducing my good friend, Tom Berger. Tom's the executive director of the Space Weather Technology Research and Education Center at the University of Colorado Boulder, which is a NASA-funded center of excellence focused on advancing space weather. So Tom, if you'll join us along with Enrico. Enrico and Tom are together, sharing a nice little seat there at the table. Together, nice and cozy. Enrico is a research scientist at the University of Colorado Boulder, also, and at Queen Mary University of London. He's also the editor-in-chief of the JGR Machine Learning and Computation Bulletin. So thank you both for joining us and being here together. And we'd also like to welcome Sujit. Sujit, if you could join us up on stage with us here now. Make sure you get up here. Great. There you are. Good to see your face. Sujit is a principal research scientist at NASA. So let's jump right into it. Tom, Enrico, you guys are there together. Why don't you share between the two of you? What are your thoughts on what you just saw from Team Solar Wind? Oh, you are muted, I think. Either you're muted or we're not hearing you, Tom.
There we go. How's that? Testing.
There you go.
All
yep.
right.
You're
So
good.
we're both in London at the Trillium offices, and it's good to be here live. Lots of thoughts on this. I'll let Enrico start in with the machine learning approaches, and I'll pick it up from there.
Yeah, hello everybody, and thanks for having us. First thing I want to say, kind of following up what Scott just said, I want to put my hands on this machine learning ready data set. Just give it to me because I mean, I fully agree. 80% of my time is spent. When I get to start on a new project and I look at the data, say, oh no, this is just a messy data set. I'm gonna spend so much time just to clean it up. So that's really a very valuable contribution for the community. That's for sure. So yeah, very excited about that. The whole project is really exciting. I mean, I've been working on solar wind kind of structure and classification for a while, and has been pretty much a kind of an open question since the solar wind has been discovered by Parker, basically, I don't know how many decades ago. What are the different types of composition of the solar wind has been an open question forever. So this project really is a kind of stepping stone to kind of understand why solar wind quantities and observable span several range of magnitudes, why again they come in different shapes and forms, where does the solar wind originate. So all of this stuff are important questions for heliophysicists that this project definitely helps kind of getting closer to a final answer. Another thing that I think it's very exciting from somebody doing space weather is that, again, another open question is how different types of solar wind are geoeffective or not. So what is the geoeffectiveness of different types of solar wind? And having a clear classification is kind of the first step, so that when you see solar wind of type A versus type B coming in, you already know that something along the chain of space weather is going to happen. So yeah, congratulations to the team. I think this is very, very exciting work that is going to open a lot of further future possibilities for research, for sure.
Excellent. Tom.
Yeah, picking up on that theme that Enrico just mentioned, once you classify the solar wind and what's coming in, the next thing you need to do is use that as your driver for other models in space weather. And the key thing about space weather, of course, is we're trying to predict the future of a given complex system. And we have just gotten a NASA Center of Excellence called the SWORD Center started in Colorado and also in Michigan, Iowa, and University of Alaska, NCAR, in order to study the upper atmosphere of the Earth and try to predict what happens to the thermosphere and the ionosphere as it receives this buffeting solar wind input. You can't predict that kind of a complex nonlinear driven system unless you predict the driver. So this is a big stepping stone to predicting that constant driver of the solar wind as it impacts the magnetosphere, changes the ionosphere, changes the thermosphere. So this is really exciting to see from a sword center standpoint, because if we take this one step further, then we can just directly integrate the predictions from this model into the ionosphere thermosphere models that we're developing for predictive effect that will be hopefully transitioned to operations in places like the Space Weather Prediction Center at NOAA or the UK Met Office here in the UK.
Yeah. And Sujit, I see you nodding your head. What are your thoughts on this? And by the way, Sujit, best flex of the day with most awesome whiteboards behind you. Well done, my friend.
Oh, thanks. Yeah, I just keep it a bit dirty in terms of discussing things. But I think I'll try to bifurcate today's presentation in two parts, fundamentally, right? One is obviously the conceptual part that we're looking from the solar wind aspect, right? But I think one of the noticeable pattern that we want to see here is that the team uses the SDO-FM, right? A foundation model that has been pre-trained on the SDO data set, and through that pre-training, you're using the embedding in order to do these challenges, right? Or do these downstream tasks. Now, this enables the whole you can consider the Helo community in order to look at the potential of the AI-based foundation models in order to use their own downstream. Now, this model, when it was designed, it was not specifically designed for solar wind, but it can adapt to solar wind, right? And as we saw in the presentation that, the researchers were telling easily that they were trained on the SDO images, and the model has to predict that from the images itself, considering it's a time series, right? So the model intuitively understands the mechanism behind, or you can consider the partial differential equations or things that is controlling the solar wind behind it. Now, the truly model understand the fundamental nature of that PD is questionable, that we know that neural networks tend to understand these relationships, but they might be represented in a different fashion. But they are the data-driven approaches, so they can actually mimic the other equations that we have seen in fluid and hydrodynamics, like Navier-Stokes, or variants of Navier-Stokes and other stuff. But in the case of Earth modeling, it's pretty common, and we have huge, immense amount of data and a lot of research to back it up, and we understand, let's say, maximum of what we are looking at. In heliophysics, that's not the truth. So maybe it's like, you can say that, I don't know, I don't want to create conjecture here, but let's say that you understand 10% of the processes that is happening over the sun, and 90% you don't understand, or you don't understand the equations that are behind it. So these methods can also enable people to do some scientific discovery, because they can let you enable the simulations and patterns that is coming up. And maybe the scientists, when they try to use these models, they will be able to find the relationship between these variables and come up with probably a new theory, or the relationship that is being justified. That also brings another caveat, that whatever the model is producing should be thoroughly checked with the relationship of uncertainty, because you don't know if it is something that model has seen a lot of time, which is for the quiet sun, or since it have just seen, let's say, the solar wind related data set, it just understands that and doesn't understand anything that else is happening. So it might create a confusion states on the neural network from those paths. So, but it is fundamentally, it was a really good work. And it opens up a plethora of paths here for the people to try out these foundation models and try to use for their own applications. We are also launching our own foundation model next week, which is Surya, which is the solar foundation model trained on the native resolution of the SDO, or 4096 by 4096. So really great to see people using these in sort of a low dimensional space of embeddings, and then trying to get to the downstream tasks.
Yeah, thank you. Good stuff. And you referenced SDO-FM, and Scott, can you imagine observable universe FM?
That'd be a big one. Yeah, I think, but I love that. Sujit, I see some PDEs behind you on the board, and just how you just I just love how we're starting to look at these things where we can use piecewise nonlinear approximations through these foundation models, and it's almost like back in Katherine Johnson in 1960. How she got giant planet to burn up, basically using Laplace, basic approximations. We're now being able to use it for science. And I think, Sujit, what I'm hearing from you, and also from you, Tom and Enrico, is that these are actually very helpful now in doing and making sort of scientific predictions that you could actually downstream. And you're almost assuming that these approximations now are a normal part of science. It's fantastic to see. Considering
really
this is all, considering that Stanford paper, 300 authors, it's crazy. On foundation models was like, what was that, like 17 or something like that? It was not that long ago.
Yeah.
Right? Or 2020. I don't know if you all seen that paper, but it's like The first 2 pages are just the author list. You know?
Yeah. Okay. Well, hey, thank you, all of you, for joining us here today and providing a few of your thoughts on these things. We are sincerely grateful for your participation, and we're going to move along to our next team. So if you will get ready, Team Ionosphere Thermosphere Twin, we'd love to hear from you. Please take it away.
Welcome everyone. We are the Ionosphere Thermosphere Twin. Before we dive into the challenge, here are the researchers, Michael and me for the science side, and Linnea and Liz for the machine learning side, as well as the faculty and advisors whose efforts have made this project possible. Now, in the last decades, modern society has become increasingly dependent on complex technological infrastructures, both on the ground, in the air, and in space. Many of these systems, such as GPS, communication satellites, and power grids, are highly susceptible to disruptions caused by solar activity. These disruptions can pose serious risks to the reliability and safety of our systems. Let's look at a few relevant examples with Michael.
Thank you, Simone. The ionosphere has a major influence on performance of GPS systems, so we're going to take a look at that. Our skill at forecasting ionospheric events must keep pace with the exponential growth of GPS-related devices everywhere in our lives. Reliability and high accuracy are required to support the growth of aviation, agriculture, construction, and transportation sectors. Currently, the agricultural sector shoulders $30 billion of losses due to GPS errors in planting, fertilization, and harvesting. And in the construction industry, mistakes must be torn down and rebuilt. GPS errors alone drive $88 billion of losses. But beyond financial losses, there is real, life-critical impact to society today. Dense, transatlantic routes are established to coordinate high-traffic demand. These routes depend on GPS accuracy in order to hold allowable safety margins, and an unexpected ionospheric event forces pilots to rely on their internal navigation systems. These systems cannot satisfy the required safety criteria for positional knowledge, presenting significant risk to pilots and passengers en route.
Thus, the final link that connects the Sun and our planet is the ionosphere, a region of the upper atmosphere extending from about 50 to thousands of kilometers in altitude, and is partially ionized by solar radiation. The dynamics of electrons in this region are influenced by various factors, including geographic location, solar wind, and geomagnetic activity, and can lead to phenomena called geomagnetic storms. One of the most informative and widely used observables of the ionosphere is the total electron content, which quantifies the total number of electrons along a vertical path from the ground upwards. Here we show a sequence of TSE maps generated by the Jet Propulsion Laboratory using a Sunlock reference frame. These maps serve as a foundation for building data-driven models of ionospheric behavior. Now, given how critical it is to predict the ionosphere's behavior in order to safeguard our system, we began our challenge with a simple but ambitious question. Can we forecast the total electron content?
Yes, with the support from Google Cloud Computing and machine learning, we did. So essentially, this is a big data problem. We're working with over 1 terabyte of data spanning many different sources, formats, and cadences. It was a crucial task to get all of these datasets cleaned, aligned, and ingestible by our model, be it for a forecasting, nowcasting, or classification task. And on top of that, we needed to be able to pick and choose which datasets we wanted to use to train our models in order to best determine which data streams are crucial for our problem. So towards this, we have developed an ML-ready data product that will be made available for the community to help accelerate future research in heliophysics. So now, given our data product, we needed the full ML pipeline to make use of it. In developing our framework, we've opted for a modular design. This allows us to easily switch between different ML models in the middle, enabling us to prototype multiple TEC forecasting models with hundreds of millions of parameters in parallel with the same code base. So to name the main three we've been focusing on, we've developed an Ioncast LSTM, a long short-term memory model, Ioncast SFNO, a spherical Fourier neural operator model, and Ioncast GNN, a graph neural network approach. In developing our models, we were inspired from previous works in weather modeling developed by our partners, namely Google DeepMind's GraphCast and NVIDIA's ForecastNet. And now I'll pass it off to Linnea to talk a bit about the results.
Thank you, Halil. So on the screen before you, you can see a comparison of the state-of-the-art empirical model, the international reference ionosphere shown here on the left, with our ground truth JPLD maps shown on the right. And we present a quiet ionosphere event on the top, a moderate storm event in the middle, and a severe geomagnetic storm event on the bottom. And so these events can be used to evaluate our models. And we can see that Erie closely follows the Earth's magnetic field, but it fails to capture the non-hemispherically symmetric structure of the ionosphere that is present in the ground truth JPLD maps. And we can compare the performance of our baseline LSTM model trained on the data package that Halil mentioned against the Erie model and the ground truth. And the LSTM model forecasts over a 60-minute lead time, so it's looking an hour ahead. And we can see that it captures this asymmetric hemispheric structure of the ionosphere much better than Erie does. However, it is not quite a fair comparison because we take in very different input data to the Erie model, and the Erie model is not a forecast model. And we can compare the performance of this LSTM to our spherical FNO model, inspired by NVIDIA's weather model ForecastNet, which captures the general motion of the ionosphere very well, but we can see that it fails to capture some of the smoothness that the LSTM model does. And finally, we can compare this against the performance of our graph-based model, Ioncast GNN, which is inspired by Google DeepMind's weather model GraphCast. And we can see that this model outperforms the LSTM and spherical FNO models by having a lower root mean squared error value, which is the white value listed on the bottom right of each plot. And we can see that it captures the general motion and asymmetries of the ionosphere very well. And while all of these models are performing very well at forecasting TEC over a 60-minute lead time, we are actively training and interested in improving our models to forecast over much longer horizons. So here on the screen before you, you can see the ground truth JPLD map on the left and the Ioncast GNN model on the right, predicting over a 12-hour forecast period. And we can see that it does quite well. And so we are really looking forward to seeing the next iteration of results produced by these models. Thank you, and I'll hand it off to Mike.
Thank you, Linnea. I invite you all to take a look at our work, just a quick peek. You can take a picture of this QR code, and I'll summarize our achievements during this sprint. We have curated a novel database that brought together diverse sources and structures of data. The data is machine learning ready and will be provided for the community to leverage and train their own models. We also built an operational catalog of NOAA solar events, categorized by both strength and duration. And we have completed building a machine learning framework that allows us to continue to evaluate various machine learning models, but also enables future researchers to leverage data sets, training and validation, as well as test infrastructure. Our Ioncast provides a novel ionospheric forecast model. And we were able to accelerate and expand our work by integrating data packages from Carmen and SDO, some past projects. And we are actively integrating our models with future projects and current projects like the Orchestrator project. Finally, as we see our models improve with more training, future work would look towards integration with NCAR operational models and other deployed models. So thank you for listening.
Atmosphere. Scott, it's got to make you feel good when you work for the company that's making some of these things possible, right?
Yeah, we just, I mean, I using the graph model. We just put that up on Google Cloud, from DeepMind, and we're getting a lot of traction around it. We have a new focus on AI for science, and one of the first things looking at is weather. And I just like to see what they've done. And I was rooting for LSTMs and Schmidhuber. As you started talking about that, and then oh no, here comes the graph model. And I feel for them. But it was just great to see that result, and I like how they directionally it maps really well, right? You see sort of this diffusion, which isn't quite accurate, but it shows you the hotspots.
It
And I'm
does.
wondering if scientists, is that enough? Is it
Well,
enough to know you've got the storm? So we'll talk
let's
to the
bring a
scientists.
couple up. Uma and Olga, if you'll join us up on stage, please. Olga is the supervisor of the Ionospheric and Atmospheric Remote Sensing Group at NASA JPL, and Uma is a data scientist and technical group supervisor at NASA JPL. So I don't know if you just heard Scott's thought here. Scott, why don't you share that again, and let's get the answer to that question.
Yeah, this is really for Uma and Olga. Is that what we saw is that if they predict farther in the future, right? They have the models and they get more diffusive. But if I looked at them just eyeballing it, it looked like it's almost on point in terms of the level of severity and the locations. I'm wondering, is that sufficient of like an early warning system for what you're looking at? Because as you go forward, you get to sort of this diffusion in the models, but maybe that's enough to detect something that's coming. And I'm just curious about that.
Well, I'll defer to Olga about, sort of what the heliophysicists need from the models.
Okay, let's kind of divide conquer. So I would say that I'm amazed by this result. I mean, it's great. I think it surpasses anything that I know for TEC forecasting, and it's absolutely needed for community, not only for scientific community, but for society in general. And heliophysics, especially ionosphere, is part of a nested system. So basically, you need kind of to figure out how from a sun through magnetosphere to the ionosphere, it's all interacts and impacts TEC. And I think that maybe it cannot yet predict 12 hours ahead those fine features, but if they show magnitude of intensification and fairly good location of it, that's already very important and something that you can build upon. I'm pretty impressed.
Yeah.
And I'll just jump in from the machine learning side. I mean, I have to say that, and we've had the pleasure of working with this team, as an advisor going through it, and they've accomplished a ton of work in a very small amount of time. I was really pleased to see sort of like the side-by-side comparison of these like different models using different architectures, and understanding sort of relatively like where is one doing better than the other. So that's something that we get to dive into, a little bit more in the last remaining weeks. But I would say that, we're kind of sort of eyeballing results, in this forum here. So everything really looks good, but, as good data scientists, we're going to go through and look at like, what are the results at the different latitude bands, looking at all these, breaking down the results by all these different factors, looking at, I know they have plans to look at, what is the RMSE for lots of different like storm magnitude events. So when we get into those meaty details, I think that's where we'll really get the insights and see like which model, where the biases are on these different models.
And the stakes are pretty high for this stuff. Getting this right really matters. Yeah, I served for a year on John Deere's Advanced Technology Council. And as you probably know, the recent magnetic storms from last year, I should say, they caused some issues with autonomous systems and systems that are even off a little bit when it comes to things like agriculture, which is one of the most important technologies on the planet, is the things that feed us, of course. And the cost was in the billions of dollars because of something that we weren't able to predict with enough time to let people know about. And there's so many other examples of why this is as important as it is, and having these reliable digital twins.
Yeah, I think Jonathan, you talked about for John Deere, I'm thinking about my laundry folding robot. Does it have to stop doing the laundry because of one of your storms? So I'm just, please get this done so I can get my laundry folded. That's what I'm thinking about. Yeah.
Let alone the harvester feeding the world.
Right.
It's extremely important for reliability of communication, for reliability of even satellite positioning. But I would like to highlight that I'm really happy to see how team worked with often sparse data set, with data sets with high and low fidelity. I think it was extremely complicated and something looking forward to, because we're going to ingest more and more data coming from cell phones, from individual users, and we need to learn how to do it in a smart way so it can really improve our focus.
Yeah, it's a great point, Olga, because so much time these data are very sparse, but these foundational model approaches are fascinating. If you can get that to work, and now you can find inferences on sparse data that are scientifically accurate, that's extraordinary.
Yeah. Any recommendations for the team? Anyone having heard their presentations, or words of encouragement?
A lot of encouragement. Great work.
Yeah, they've done, I think for me, I've kind of already spoke to it, but like, let's go deeper into the errors now. Like, let's really understand them. Let's try to understand the differences between the models. Those are the types of things that become really important. Like when you run these systems and operations, when a storm is missed, right? That's when the scientist wants to understand, well, why was the storm missed, right? So these questions become very being able to get the answers to these questions, or at least being able to anticipate them with like really good validation, is important.
Yeah.
But they're very impressive results. And I think really it's the speed of these methods that is really the enabling capability here. So, I mean, we would love to plug these models into and start exploring like the what if scenarios if possible, right? In order to understand and really make this like digital twin capabilities possible.
Yeah, and I'd like just to pitch in what Uma mentioned. That's probably we need to validate separately low latitudes and high latitudes, because physics are very different and coverage is very different. Something to work on.
Yeah. Okay, well, thank you, Olga. Thank you, Uma, for joining us here today. We're going to move on now to our next presentation. And at the beginning here, Leika knows she's not supposed to have a favorite when it comes to these, at least at the beginning, because, you want everybody to feel like they're equally loved. But she did highlight this next team. So if you will, pay particular attention to the truly remarkable and astounding work and goals of Team Orchestrator. So Team Orchestrator, if you would, please take the stage. Oh, but before we do, we will have an introductory video right before the team intro video from James Walsh, who is the faculty lead for Team Orchestrator. And in this video, James will set a little bit of the scene for what the Orchestrator research team is working on.
The next presentation is a slight departure from what you've seen so far. As the world has been tracking, there's been a ton of interest in applications of large language models, or LLMs. One of the ways this particular category of foundation models has been developing is through employment under agents. There are some varied definitions for what exactly that constitutes. So, as context for the next presentation, we're going to take our partner Google's definition from their agent development kit. An agent is defined as a self-contained execution unit, designed to act autonomously to achieve specific goals. They also use the term subagent to note when one agent can ask another to complete a task. To give an analogy, consider a work group chat, memes and lunch decisions preferably excluded, a common scenario where each individual has a role in a set of responsibilities. If you imagine the team leader in the chat asking for something, a role of one member of the team might be to break that down and contextualize it for the other members. Say the team leader asks their team to help organize a conference. A project manager role would break that request down, perhaps into allocating someone to invite the keynote speakers, a ticketing officer, someone to design the graphics, and maybe even get a website online. In this case, each role could be an agent. Having access to an image or website editor in the case of those latter roles can be integrated through tools. The Model Context Protocol, introduced last November by Anthropic, is the USB-C standard of how we make tools available across swarms of agents. They provide functionality to execute in predefined ways, like creating the infrastructure we'd need for a website for this hypothetical conference. Coming back to our group chat, if this is all happening in a chat room where everyone is made aware of each message all the time, we label types of interaction like these as a type of communication pattern. In a group chat, this isn't anything fancy. Everyone is broadcasting to everyone else. But there may be more interesting communication patterns for different tasks. If we want to go one step further and be more realistic, we would consider both agents and how they interact and step up to calling that a design pattern. There are many ways to engage with models under an agent, and the typical rules of substitution apply. In the LLM context, that includes things like fine-tuning a pre-trained base model for improving task specificity, tuning prompts or rewriting tools for greater suitability with the chosen base, or providing a suitable knowledge searching capability. A little like letting your agent Google things for you when it's thinking through a response, via retrieval augmented generation. Orchestrator has developed a means to both create and apply new design patterns for evaluation in some heliophysics tasks you'll be familiar with. So, without further ado, please welcome the team.
Hello. You'll be delighted to see what we have built here in the Orchestrator project. We have, as the team, we have myself, Russell, and Kevin as researchers, and we have James and Will as our faculty members. The Heliolab vision is to reframe AI and data from point solutions to network intelligence. We can orchestrate AI products like Lego to make a full picture of the solar environment. Wouldn't it be helpful if we can orchestrate AI methods, like all of the awesome FDL projects, as easily as saying tea, Earl Grey, hot? Well, that's exactly what we're trying to do. Introducing Heliolab Orchestrator, an agentic orchestration engine for heliophysics queries in natural language. We can ask in natural language for simulations of active regions of the sun from the Arcade project. It orchestrates, and it gives the results of the Arcade team's models. We also just saw the presentation from the Ionosphere team. How about a calculation of the electron density profile in the ionosphere under the IRI model? Once again, it orchestrates, and voila, the electron density profile. But how does it actually build these beautiful Lego creations? Stay tuned to find out. Let's examine an example where we asked it to create a data pipeline for model training. After some back and forth for clarification and an approval request to actually go ahead and create the infrastructure, it produces the pipeline. This is the instruction manual for the pipeline it created. It includes infrastructure and code for downloading and calibrating data, as well as model training and evaluation. A human in the loop is required for granting approvals. But who creates this instruction manual? Why, the master builders, of course. We have the new master builder approach to systematic research, which is our mechanism that we wish to measure. And then we have the new master builder reasoning with a star benchmark dataset, our yardstick. How does this new master builder approach to systematic research work? The master builder unlocks the potential of Google ADK for science, with agents and sub-agents in different agentic design patterns optimized for specific purposes. Supporting these agents, the master builder has MCP servers, including a super gateway bridge server and extension tools. To communicate with the master builder and access the system, we have a natural language UI and transparent logging. To that end, this is the Orchestrator's web interface. In the center, we have the chat window, showing prompts, agent replies, and local tool activity in real time. Below that, we have the infrastructure monitor, depicting the infrastructure created, giving warnings about possible memory and credit overloads, as well as system logs. On the left, we have the session list, where each run is tracked with a unique ID, and switching between sessions is easy. And on the right, we have we keep a record of approvals and system events, so the human always stays in the loop. Now that this system is available, how do we know that we're navigating around it well? Do we have the right yardstick? I'll pass the mic to Kevin here to discuss this master builder.
So the whole field is learning a treasure trove of design pattern, but not yet for heliophysics, that caused us to create a reasoning with a star dataset. Our answer is to bring this new type of agentic reasoning to space science. Surprisingly, we discovered a way to use NASA's Living with a Star program problem sets for the heliophysics summer school for LLM reasoning. It consists of heliophysics questions and answers in PDF files across different topics, and we convert these files into JSON lines format in our reasoning with a star dataset for LLM reasoning input. We can use Orchestrator to decompose a query, assign expert agents, and log each step. But we also need a way to evaluate these approaches for science domains systematically. It's heliophysics for AI, both guiding Orchestrator and giving us a way to measure our agent development progress. And since we have created the dataset, how do we benchmark it with different agentic architecture with a query in our Orchestrator chat? That brings us to here. We turn a bunch of agentic design into a dependable system. For the heliophysics benchmark use case, Orchestrator prepares a dataset for 2 agentic design patterns. For example, the first pattern uses cooperative workflow through physics-aware and math-aware experts to inform the summarizing agent. And the second pattern uses the hierarchical workflow from the higher to lower hierarchy throughout the process. Both patterns will return their answers. And the system scores the output based on the accuracy, latency, and resource usage for the comprehensive report. This allows the system to learn which pattern works better, so it can select the most suitable architecture next time. And we created 4-agent architecture. Here's one architecture we named PACE. This is a simple design pattern which solves a query through plan, answer, critics, and enclose. Each task is broken down into smaller plans with acceptance check. If the system does not pass the acceptance check, it will return to the solver one time before the system outputs the final answer. Other architectures also employ similar ideas. For the multi-agent patterns we design, some are able to do self-refinement and allocate domain experts. However, we'll go through them in detail at the technical showcase. We compare our agent architecture across 3 domains: math, science, programming, with 6 datasets. We evaluate our architecture with Google's Gemini 2.5 Pro. In the mathematical datasets, all design patterns converge, with PACE marginally more performant, at least compared to more complex architectures, i.e. GSM-AK and math. This means simpler architecture is enough. And for GPQA, the PhD level problem sets in physics, chemistry, and biology, Face's hypothesis generation capability helps improve the chain of thought in the reasoning task. In human eval and SW bench, performance varies by the coding task type and by agentic architecture complexity. Now we want to check this architecture against our heliophysics dataset, reasoning with a star. And this is where, all without retrieval of domain-specific knowledge, what James said about an agent's ability to Google things, which you expect to boost these results. Analytic design, especially schema and face, perform better with the unfamiliar heliophysics query. We also conducted performance analysis on reasoning with a star based on the heliophysics and math categories of each problem set. We're excited to share these in the upcoming technical showcase. And summarizing the result, there's no one-size-fits-all design pattern. Our Orchestrator should choose the design pattern to match the task.
With the Orchestrator system, we can compose other machine learning models, physics simulations, and data pipelines that previously took weeks, months, or even years into just minutes to prototype. This significantly helps scientists focus on the research aspects instead of the technical toolings for space research and operations, while keeping humans in the loop to verify the augmented process. Heliolab Orchestrator, the future of scientific discovery. Thank you.
Most excellent team Orchestrator. Thank you for that. And what do you think? AI Legos, Scott, is that a thing now?
Yeah, why not? I love that caricatures they've got. I mean, and also they're being kind. I think these the technology is evolving so fast, Jonathan. Controlling these sub-agents, they do probabilistic reasoning, and it's not as simple as asking it to print. It makes up its own mind. And I think, and trying to figure out how to bring in these probabilistic reasoning into scientific progress is a great step forward. And
yeah,
I love what they've done with the MCP servers and everything else. It's a great step. Yeah.
Yeah. Okay, well, let's bring up our next panel here. Richard, Xing, and Matt, if you'll join us on stage. Richard is a Principal Solutions Architect, AI and Analytics at Pure Storage. Xing is an astrophysicist at NASA, and Matt is the Program Executive for Data Science Innovation at NASA. Thank all three of you for joining us here today. Matt, why don't we start with you? What did you think of what you saw with the Orchestrator team here today?
Well, thanks for having me. No, I think the Orchestrator thing is fantastic. I really did appreciate the presentation. I love, first of all, I love Legos like anybody else. I have Legos on my desk that I play with. So the Lego comparison is accurate. I think any of us who have put Lego sets together can value, the sub steps like we talk about, where you have like a whole big model of, let's say, a truck, and then you learn how to put together the bumper and then add it in. So a lot of ways the Orchestrator works like that. And I think if we look at where all these AI agents are going, I know which model I like for coding and which model I like for doing math and which model I like for writing tasks. But having an orchestrator that works like the Lego blueprint for all that is really, really a cool innovation. And I'm excited to see where it goes in the future.
Excellent. And Xing, from a physics perspective, what do you think about what they're trying to do here with Orchestrator?
Well, I think it's great. It's good and bad. It's bad in the sense that it might put us out of our job.
You think? That's, I've not seen on the lists. Everybody's publishing lists of here are the jobs that AI is going to eliminate, and I have yet to see heliophysicist on that list, but I guess who knows? I guess that's possible.
Well,
Yeah. Richard, how about you? What are your initial thoughts, feedback on Team Orchestrator and what they're doing?
Yeah, I really like the project. It's really forward thinking, and I also really like the emphasis on the evaluation framework. To really evaluate all the components of these systems. I mean, and also, yeah, the Lego building blocks of the components. That's a great analogy. I might steal that from you guys if you don't mind. But no, the real challenge when it comes to these kind of agentic workflows that a lot of people are sort of grappling with is, it's great to kind of put together cartoons of all these components. Like this master one is going to be the heliophysics component, and then this agent's going to be the data sort of curator. But the real challenge is really in evaluating that everything is doing what it's supposed to do, because it could be that maybe one model you want to refine it further, or maybe you want to have a smaller model, maybe more kind of isolated, like focused model. But how do you really evaluate that every model is doing its job as it's supposed to? Hint here is that you cannot expect that the model is always going to perform exactly what you want it to. So I mean, I really like how the group is thinking about this evaluation framework. And thinking about really kind of keeping up with what's happening every step of the way and having the human in the loop. So I think that's key to having like a practical production level system deployed on these with this framework.
And Matt, what do you think is necessary to unlock the potentials for what we think about agentics and where things might go? What do we need to do to get to that vision?
Oh gosh, a lot of steps. I think I love the discussion on metrics. I think Scott made a really good point when he came in here about probabilistic models. I think one of the things that's important from a science perspective is that if we use these agentic workflows and each one of those have a probabilistic output, that we have reproducibility so that we can trace it. It's one thing to find a new discovery, but we have to make sure that it's reproducible. So I think those are critical steps. I think another important part of this, and Xing kind of hinted at it, is the idea of trust. Scientists will use these tools, so we have to trust in them and make sure that they're producing results that are scientifically valid and accurate. And we're also not worried about them taking our jobs, but also that it actually enhances the scientific method and making our work better and showing that sort of value. So what are those sorts of metrics to how they improve my workflow as a scientist?
I'd love to spend a couple minutes talking about trust at this point in the presentations, because it is such an important thing. And I'd love to hear from you, Xing. What's it going to take for you to trust these tools as a heliophysicist, as an astrophysicist? Oh, I think you're muted, Xing. There you go.
Okay. I like to pick on another theme, and that is common throughout all the presentations, and in fact, a lot of the AI work is based on, which is data. We all need data, and data produce whatever result we see through whatever approach or tools that we use. So the question is, how do we know that we're actually using the data correctly? You know, garbage in, garbage out, and that's a problem. And that's one of the things that, in fact, we are trying to push and make sure that all the data are accessible and reusable. So the so-called FAIR principle. So in terms of the agentic approach, you have agents, but how generally they can be applied, or all the agents communicate differently, or how do you get all the pieces to talk to one another correctly?
Yeah, I think Xing adds to that. If you look at there's just a rapid pace in ML. Papers are coming out so fast, Jonathan.
Yeah.
And the question now is like, is it reproducible science?
Exactly.
Right? You see the papers, you see the equation, and if you try to actually reproduce it, you're like, I can't do that. And so maybe now, Matt, to your points, is like, could we now do the combinatorics where as you publish a paper, you now publish an MCP server and saying, go have it, use this in NASA. So now you can actually, imagine what that does for the rate and pace of science as well, Xing. And then especially if, you can validate the data for this, you can now, when you publish the result, you can actually publish another Lego block, if you will, right, for people to use. And I'm really looking forward to that day when that's the pace of science. Right.
Yeah. Yeah. Anyone have any thoughts on concerns in the short term as we move along towards all that?
Yeah, I had a point to bring up. So if you look at a lot of people that are leveraging large language models or whatnot to actionable insight or whatever, it typically requires a bit of fine tuning for their particular use case. I think I wanted to also kind of challenge the group a little bit to think about what does fine tuning look like for agentic systems. So think about maybe fine tuning all models in conjunction together for some overall use case. I think that this is kind of like on the bleeding edge right now of kind of meaningful deployment systems that you could really rely on and trust to perform an entire workload. Consider fine tuning on that entire workload, all the models in conjunction. It's a non-trivial task, but that's where we're seeing a lot of real meaningful work in the space.
We're seeing that above. We have this thing called Alpha Evolve, and you're starting to see things like Monte Carlo tree search and genetic algorithms now being combined with the stack.
The stack, yeah.
And so the stack themselves is they're going to be almost like the TCP/PI stack all over again, right?
Yeah.
But now you have that stack of models. Can you learn above them? And some of the learning is actually being expressed in English, which are astonishing, right? And now you're starting to combine good old-fashioned AI with that. So I think there's a wide open area, Richard, in terms of how you combine these. And we ain't seen nothing yet.
We ain't seen nothing yet. And let this be the pioneering project that shows how you can use this in science. I think it would be really compelling.
Yeah, very cool.
We had invited Vint to be on this panel today, as a matter of fact, but he had too much going on, and so would be interesting to get. That's his Vint Cerf, of course, the creator of the TCP/IP stack, or one of the creators of the TCP/IP stack.
He's like, what all is new again, right?
Everyone's throwing around this analogy now with TCP/IP stack. Yeah,
you get it though, right? The 7 layers. You got
absolutely.
the model, Lyra model. You got all these different models, but I think they're all coming together. And then I think your point is right on. Is like, how do you learn above that? Because we all have our own stack, the humanoid form, but how do we learn above that through experience? And that's
fine tune, train the entire system. Yeah, like how to go about it.
Yeah, train the stack. Awesome.
Train the stack. That's a new T-shirt. We're really good at T-shirts here in Silicon Valley. So
train the stack. That's
train the stack. Yeah. Okay. Well, thank you all so much for joining us here today for this panel, and we're grateful for you taking some time today to provide some of your thoughts on all this stuff. We are going to do one final panel today. But before we do that, I want to say thank you to all of the researchers and all of the faculty. You did a bang-up job today on your presentations. And we want to do that final panel that is going to reflect a little on all the things that we've seen. So if we could bring up Leika and Lucas and Matt, we're going to bring you back up again. Here, I believe. Lucas is a program manager for Earth and Data Science and Technology at NASA JPL. And I think they're looking for, there you are, Lucas.
Hi.
Welcome. Good to see you. Okay. And if Matt's still here and going to join us, that's great also. Okay. I'd like to start with you, Leika. I used your name several times today. I can't help myself, you know, it's all those great conversations we have about, you're so nonchalant about, well, sun is everything, Jonathan. It affects everything. You're never fazed by anytime I want to bring something else into the Helio discussions. You just, of course. Why wouldn't
you?
You?
Mean the dark matter and all those other gobbledygooks?
Everything.
Like they matter?
Yes, exactly. Well, what do you think, having seen the presentations from the 5 teams today? Any thoughts that you'd like to share?
Well, look, remember, I think we have to put this in ChatGPT. Earlier, we were talking about how our vocabulary is being limited to describe the rate of progress we are seeing. So, just merely saying amazing, excellent, bold over just doesn't cut it. And I haven't prepared. Didn't ask ChatGPT, give me some new words.
Try Gemini.
All right. I will try Gemini.
Okay.
and what, so we've been doing this for 10 years. And what I'm seeing is really the accelerated rate of progress. I mean, I didn't imagine we'll get here so quickly, but it's not even quick enough. We are only limited by resources, in this case, compute resources or, green dollar resources, because we could be doing a whole lot more. I think scientifically, I have some hope, right, from seeing all this. I hope that these tools and insights sort of ripple out, all of the stuff that our exploration ambassador was talking about into missions, models, and operational readiness. There's so many examples there. And I hope that they help us build heliophysics that is not just beautiful, but useful, science with relevance to life and society, essential to living in a sun-influenced world. There is no denying. We have to kind of understand this system, fix things we can fix by really creating a sharper image of the system we live in. And I think each one of the models kind of threw out these curveballs that you can pick up and you can take it in so many directions. And, you ask Scott, and he'll give you near infinity variations on each one of those. And mathematics can actually do that. But there is a cultural component I felt out of this, that this sort of inspires a shift in how we do science. That's kind of just as important. Our approach to doing science hasn't changed in 200-300 centuries, I'd say. Like, we are in the first quarter of 21st century, but we are still using old tools and techniques. It's very clear that we are practicing more interdisciplinary science, more experimental, more welcoming to new voices. That's what these approaches are teaching me, especially those who speak fluent data and discovery at the same time. I mean, that's my learning from what I heard. It's really pretty awesome, but it's just the beginning.
Yeah, it really is. Yeah, it really is. And on that note, I think that you said something that was really good there. The notion of hope for how this will ripple out. And I'd be interested in hearing a little bit about the personal hope from all of you here about how this and this type of groundbreaking work can and perhaps will influence the broader scientific and global community, heliophysics and beyond. So Lucas, if I can start with you, feel free to reflect on anything you saw today, but what do you think? What do you hope happens? What do you expect might be able to happen?
And I saw so much that I could talk on, so I'm really having to condense down everything I'd love to share. And I want to riff off something that Leika also said. The way that we've been doing things for a very, very long time compared with how we could do them, the different science domains are the same way. Earth science has spent decades taking in dense observations and retrieving and inferring very detailed parameters of what's going on. That's because to validate them, you go in your backyard and you look around. It's very easy. And heliophysics is trying to solve a problem like that with a few point spacecraft in the middle of a giant 4D changing field with EM fields and particles and fluxes and a complex sun. That's insanely difficult to be able to try to do the same thing, except we are. Today, with the observations that we have and some of these new techniques, we're actually attempting that same inference problem. And we can learn from Earth science and we can also teach them. Because what we can learn from them is that you can statistically rigorously infer these important properties using physics principles. And they did. And now it's too slow and they can't afford to do it anymore because the models are so incredibly big and slow and complicated, they can't afford their own science data processing systems. So they're looking for ML the same way you're looking for ML to get them out of a different hole that they spent several decades going down into. We don't have those in existence here in heliophysics, but I saw the teams wrestling to create them and create them fast at the same time. And that's really exciting if we do it right. And the final version on that, before I let someone else talk, because I have too much, I'll eat up all the time if I don't stop myself, is that any estimate of a parameter is dangerous unless you know if you can trust it. So the uncertainty is not a fun thing you do at the end. It is fundamental to even knowing if you did a thing at all and knowing how to compare it with something else. Accuracy is meaningless without uncertainty per observation. And I saw some of these teams playing with actual uncertainty estimation. That is rare in the literature and even in other science domains. So I can't applaud that enough. And things like network dropout and stuff, concrete dropout that people do on the models ain't what I'm talking about. Yes, you get an uncertainty. No, it doesn't mean anything at all. So I'm not just talking about some spread. I'm talking about a physically measurable, validatable uncertainty. And because these teams are doing it, they're going to carry that knowledge with them as they radiate out and do good data science for AI. So I'll stop now. I have lots more to say. Hopefully you'll come back to me at some point.
Excellent insight. Thank you, Lucas. Matt, I'd love to hear from you as well.
Oh, sure. Yeah. So hopes for the future. I think, I find a lot of times when I think about AI and science, a lot about telescopes or microscopes, in the sense that these are instruments for which we can observe the world. In a lot of ways, that's the way AI is working. We're developing a new instrument for scientists to observe the world. And you could ask the question, is a telescope science? Like, I don't know. Is AI science? Like, I don't know if we could get into these debates about the semantics of what's science and not. But at the end of the day, a scientist needs a telescope in order to observe the stars. And at just the same way, we need AI at this point to look through our data to see what possibility is out there. For now, we're reproducing things that we've done in the past and trying to replicate normal processes from days gone. In a lot of ways, it's a lot like, hot air balloons and airplanes. There's been hot air balloons and it's great. I can go up high in the air and then I can see over that hill. And then somebody invents the airplane, the Wright brothers do, and they're like, hey, we can go up in the air like we did in hot air balloons and see over the hill. But the reality is the airplane enabled so much more. Now we can go over the hill. So I see AI in much the same way. We're at this point right now where we think we can see over the hill, but I'm really looking forward to all the things I can't think of that we're going to be able to do with AI that we can't today.
Fantastic
Matt,
analogy. Yeah, Leika, please.
I am going to join in because you said something I totally believe in. The AI is a tool like telescopes and microscope, literally, right? So I never took help of ChatGPT or Gemini for this word. My definition of AI is augmented intelligence, not artificial, nothing artificial about it. It's just augmenting with the knowledge of math.
Yeah.
Thank you.
Yeah, that was great. Thank you, Matt. And by the way, Marvin Minsky was a friend, and I told him for years that I thought, it has not been a helpful name that you gave this thing decades ago. But it's what we have, and I do like yours, Leika. Scott, we only have a couple minutes left. I'd love to hear some final thoughts from you about all this stuff that we're talking about and your hope for where this might go and what we might do based on some of the things we've talked about in the past and even here today.
Yeah, I think I'll leave the team with the thought here is that AI is not a tool. It's not not mathematics. It's becoming a collaborator. And I think back to your point, Leika, we have created this alien intelligence for us that's now available to everybody. And what I haven't figured out yet is how to use it most effectively. You know, we've had AI notebooks. We have the chat interface, which is the fastest growing software we've ever seen in history. But how do you actually bring AI in as a collaborator and trust it? And what can actually do science? And I think the people here who are pushing the frontiers of this, where they rattle off as though it's no big deal. I'm just doing projection of multimodal tensor spaces, and I do the following vectors. I got an autoencoder, as though it's no big deal, right? I think that crowd, I think Lucas can help us figure out how do you truly do science with AI as a collaborator, and how do we apply it to solve some of the greatest challenges we've ever seen before for humanity? And that is an open question.
Yeah, for sure. Okay. Hey, all of you, thank you so much for this. We're running out of time here. We have one more thing we need to get to, but we're sincerely grateful to you, Scott, Leika, Matt, Lucas, and all the other panelists and researchers, everyone that we've had here today. Thank you for joining us at the Heliolab Live Showcase. And as a matter of fact, if you're interested, this will be posted online. You will be able to see all this, and we'll share that information with you coming up. But wait, there's more. We are going to move into the annual Collaboration Awards. And for this, I would like to welcome to the stage another dear friend and colleague, Mike Little. Mike, if you're able to join us, there you are, my friend. Good to see your face. Matt, I'm trying to say Navteca. So yes, you're with Navteca, and you're muted, by the way, so unmute, my friend. But you had quite a career, quite a career in the Navy, but also quite a career at NASA, haven't you, Mike?
It's been a fun 70 years.
It's been a fun 70 years. A lot of wisdom in a 70-year fun time. Well, hey, we're going to do the Collaboration Awards. We're going to do them together. And this, of course, is a time where we want to recognize some of the special characteristics that teams have exhibited. These nominations for the awards came from the teams themselves. So without any more time, let's celebrate the hard work, the late nights, the caffeine-fueled laughs. It's been a journey for them, and it's a journey worth sharing. So why don't you kick us off with the first Collaboration Award?
Before I start that, I'd just like to say what an honor it is to listen to the work that these people have put in to all these different projects. It's amazing stuff. And so congratulations to all of them on all that work. And it's also an honor to be on the stage with you, Jonathan.
Oh, and I feel the same way with you, my friend.
So let me start with the most dramatic pivot. And pivoting is an action taken when new opportunities arise unexpectedly. Think serendipity. Sometimes this means starting completely from scratch after much commitment is put into one idea. And that's really hard to recognize when you need to change, when you need to pivot. The most dramatic pivot award represents these changes in direction at times unwanted, but certainly necessary. Jonathan.
And the winner is Decoding Solar Wind Team. You know, throughout the sprint, the Solar Wind Team has embraced taking risks, pushing forward towards the unknown while never losing sight of the how and why. Led by their faculty, the team made a bold pivot after already having defined and committed to an initial solution at the first formal review. This direction and guidance helped ensure the team stayed on track and resulted in a much stronger project. So congratulations, Team Decoding Solar Wind. Okay, next up.
So our next award is the Steely-Eyed Operator, which is one of my personal favorites. In every FDL project, there's a moment when everything can go wrong, and it often does. This is the implicit contract of high-risk, high-reward research. If you don't go through this, then your work probably isn't new enough. Remaining clear-eyed and level-headed in this moment is a rare quality, and without it, FDL wouldn't deliver. The steely-eyed operator acknowledges the efforts of a team member who's been regularly the calm voice in the storm.
And the winner is Multimodal Flare Prediction Team. Here with this award, we're celebrating the expert execution and unwavering focus of the Multimodal Flare Prediction Team, which has led to an incredibly exciting result, both from a heliophysics and an AI/ML perspective. The entire team, including faculty and advisors, were all hands on deck, calm and precise in execution, and relentlessly focused on mission success. Congratulations, team Multimodal Flare Prediction.
So our next award is the Unexpected Discovery Award. And just like dirty dishes helped the discovery of penicillin and melting chocolate bars triggered the creation of the microwave, the Unexpected Discovery Award represents that ability to stumble upon a breakthrough. As Plato once said, science is nothing but perception.
And the winner is, it's a joint win. It's Decoding the Solar Wind team and Orchestrator team. Like finding a needle in a haystack, the Solar Wind team uncovered coronal mass ejections that weren't listed in existing catalogs, a serendipitous finding that could have meaningful implications for solar event tracking and analysis. Chance, however, is not to blame, with the entire team, official and unofficial, pulling more than their weight. We can't wait to see what other discoveries lie in store from that team. And as part of the joint award, the Orchestrator team unexpectedly came across the wealth of knowledge and worked examples coming from with the Living with a Star summer school program. Discovering and unlocking the potential of nearly 20 years worth of high quality curated content not only provided the basis for the team's benchmarking, but also may provide a unique data set to improve AI research and reasoning much more generally.
So our next award is the Heroic Comeback Award, and this also is one of my favorites. The Heroic Comeback is an acknowledgement that when discovering something genuinely new, you first have to fail. But that's only one half of the story. Simply failing isn't enough. Getting back up, learning, evolving, and trying again is how legends are made.
And the winner is Team Ionosphere Thermosphere Twin. Faced with the daunting task of taming an unknown data set and open question, the Ionosphere Thermosphere team more than rose to the occasion. This dream team, under the crucial leadership of the faculty team, came together from day one to make it work. Whether it was experimenting with cutting-edge machine learning techniques or pivoting to new data sources, the team navigated each challenge with renewed vigor and energy, with unexpected direction leading to new insights. Of course, behind the scenes, there was ceaseless exploration and engineering, which included many late nights from the human compiler, deservedly recognized in this heroic work. Congratulations to you both.
So our next award is the Collaborative Spirit Award. The Collaborative Spirit Award is the representation of FDL's beating heart, interdisciplinary research. It supports the idea that to achieve great things, 2 or 20 minds are better than one, and that exchange of knowledge is key.
And the winner is Team Orchestrator. From the biggest team to the smallest, this award goes to the Orchestrator team, whose success was built on a culture of mutual support, integrated effort, and enabling leadership. From the very beginning of the sprint, the Orchestrator team sought to involve all other teams in their summer research, working incredibly closely. All barriers to asking questions were gone as the team moved forward with eyes on the prize. Collaboration in this context was not just within the team, but across all the teams. This culture of humility and building together has truly meant that the whole was greater than the sum of the parts. And we can't wait to see what these Lego block collaborators the team created will do for heliophysics. Congratulations, Team Orchestrator.
Yes, congratulations. And now for the Pillar of Support Award. The foundation of FDL is in its community. This award goes to a reviewer or advisor who has made an outstanding contribution to the summer research sprint, as nominated by the teams themselves. Without our pillars of support, we cannot hope to achieve the breakthroughs that the world needs.
And the winner is another joint award. The foundation of FDL certainly is community. This award goes to a reviewer or advisor who has made outstanding contributions to the research sprint as nominated by the teams themselves. Without our pillars of support, we can't hope to achieve the breakthroughs that the world needs. Yes, I just did the same thing. There we go. And the award goes to the 3 advisors who have gone above and beyond for their teams. Firstly, we want to acknowledge Uma and Olga, who we heard from earlier, who made significant amounts of time available and freely shared their expertise, even when they were supposed to be on holiday, if you remember, calling in remotely while on vacation. The third person to acknowledge is Robert. Robert, who not only contributed to 1 but 2 challenges. His inputs and stepping up was absolutely instrumental to the success of the team. Congratulations to all 3 of you.
And thanks for your hard work in making these projects successful. So lastly, the Apollo Award. And the Apollo Award celebrates the same engineering excellence that got us to the moon and safely back, an important emphasis on safely back to the Earth. In the era of applied AI making substantive contributions to space exploration, we need stringent engineering standards in parallel with innovative AI to ensure that our AI-enhanced science is safe and trustworthy.
And the winner is Team Arcade. The Apollo Award goes to the Arcade team. Not only has this team probably had the best acronym of any team we've ever had in FDL, but it's embodied what it means to be interdisciplinary and collaborative. At every step of the way, the team had the end in mind, producing interactive demos and prototyping new visualizations, all having production in mind for that end. With dedication, focus, and a clear goal, the team has ensured that we're truly ready for rigorous validation of AI ML pipelines with uncertainty quantification and physics-inspired bases. We can't wait to see what this unlocks with future foundation models being developed. Congratulations, Team Arcade. And congratulations to all the winners of the collaboration awards this year. Well deserved for all of you. And thank you, Mike, for assisting in this wonderful thing that tradition that we have. Thank you.
My pleasure. Thank you.
Okay, we have 3 minutes left, and we'd like to use those 3 minutes by bringing up the CEO of Trillium Technologies. I am live from Los Gatos, California, here in Silicon Valley, the U.S. representation of Trillium. Across the pond, we operate 2 other labs, all under the Trillium Technologies company. So James Parr, if you will join me, my good friend, colleague, collaborator. James, I know you've been watching. I see you've probably been taking some notes. We'd love to hear any of your final thoughts about what you've seen here today.
Yeah, thanks, Jonathan. Yeah, honestly, it's sort of goosebumps for me. I really, I don't like saying, we're proud, but goddamn, we're proud. It's just so good, this stuff, really. And I really wanted to thank the researchers for working so hard. It's really special work that you've achieved here. And, I heard, I agree with Leika. I love the augmented intelligence acronym, and we like this notion of network intelligence because we believe that trusted systems are multiple systems, multiple data sets, multiple models, all working in concert. And that's essentially how we'll end up with the trusted systems that we want and need. But actually, I think today was about collective intelligence. The special thing that happens when people, human beings, work together. And I just wanted to say thanks to everybody for jumping in and coming on this adventure with us. Researchers, you've done amazing work, and we're so proud, and also the partners as well. And Scott, it's been great to have you, as our thought partner, and we really, love having you guys, the Google team, and sort of every week spitballing and helping us learn and helping us be better. But also I wanted to take a moment to thank the faculty. These are sort of the faces you see on the screens at the beginning of the presentations, but these guys, the faculty, really, they're the ones that quarterback this work. They often come up and conceive the challenges, they make them what they are. And so I wanted to take a special moment to just say thanks so much for working so hard, and really performing miracles. We're really, really thrilled and looking forward to what comes next.
Excellent. James, thank you so much. And thank all of you who have taken some time to spend with us today and hear from our researchers. And of course, as everyone has been saying, thank you to our faculty. Thank you to our advisors. Thank you to our entire community. Thank you to our partners at Google, at NVIDIA, at Pasteur Labs. We have said it before and we'll keep saying it, that we couldn't do it without you. Thank you again, and we hope to see you at upcoming things. By the way, you can see all of this. You can share this with your friends. Just go to fdl.ai/live for the replay. Best, see you soon.
The FDL Heliolab has been at the forefront of advancing our understanding of life within the solar atmosphere. Through intricate interactions of magnetic fields, radiation, and plasma between the Sun, Earth, Moon, and Mars, we are now able to explore these phenomena with the power of artificial intelligence. We asked our senior FDL faculty to reflect on the groundbreaking progress, unveiling the science being revealed, and to offer a glimpse into the future of this transformative work.
In many cases that I noticed as a reviewer and then as a faculty, the results are very promising. So it does help open some of those bottlenecks that we have in the research. And occasionally, like in some of our more successful challenges, it keeps on giving. The team sticks together, keep coming with new ideas, with the right papers, they interact with the community, and then more ideas come in, which we then ourselves can use in the future FDLs. So it creates like a snowball effect, in my opinion.
I think you get ideas and solutions from this collaborative environment that one person alone wouldn't think about it. That thing is very positive. And also, I think this collaborative dynamics can bring the people from academia that is more used to work autonomously. I think this interdisciplinary way of working could help those to open their minds and have like a broader vision.
The one aspect that I really liked about FDL was the deadline system, right? The internal deadline system. The first thing that I really appreciate. I mean, it gets you out of your comfort zone. You might not realize, you might feel a little overwhelmed while you are in there, but it grows into you over time. And then you don't even realize that you are actually enjoying the process. But the weekly thing or a bi-weekly thing actually helps you keep on track, keeps your work on table, and it appropriate track of your progress.
FDL Heliolab has led the charge in applying AI to space exploration. We extend our deepest gratitude to our advisors, guest experts, and partners, and perhaps most importantly, FDL's exceptional researchers for a decade of inspiration and innovation.